103.2 Preston FM.
We dare to be different.
International researchers are a step closer to understanding the birth of the sun. And one of the people involved in the research is Proffesor Brad Gibson from the University of Central Lancashire, who has investigated the solar system's prehistoric phase and the events that led to the birth of the sun. And I'm really pleased to say that Proffesor Brad Gibson is in the studio this afternoon. So, Brad, a very good afternoon to you.
Good afternoon, Huey. Thanks very much for having me.
Lovely to meet you. Now, first of all, a very simple question. What is the sun?
Well, it's a gigantic ball of gas. It may look, when you look up with the naked eye, it may look like it's some solid flashlight beaming there, but in fact it's this hot bubbling plasma gas, and what is actually powering it is not sort of the electricity that comes out of your halogen light bulbs. It's actually nuclear fusion. So you have down in the core where it's very hot, it's very dense, you have what we would call a nuclear fusion reaction, which basically just takes hydrogen and smashes it together and converts it into helium, and when you do that, you give up a little bit of energy, and it's that energy which powers it and what we actually see. So it's effectively a very powerful fusion reaction, or a fusion bomb, if you like.
And is the sun also a star? Is it a star?
It is indeed. I think that's one of probably the most common misconceptions maybe that people have, because it is so big on the sky and so bright. It really is exactly the same as the vast majority of the other. If you step out into the country, you see these little spots of light in the night sky. In a nice dark site, you may be able to see about 6,000 of them with the naked eye, more or less. And each one of those is more or less exactly the same as the sun, just viewed from many, many, many light years away. So you're seeing the light of those suns or stars the way they appeared many tens or hundreds or thousands of years ago.
So with all that activity up there, would we, if we could hear, would there be sound coming from the sun?
There is in effect sound. In fact, we have there's an entire, much like earthquakes. There's a whole field of science called seismology, where you measure the effect of an earthquake on the Earth by effectively looking at sound waves as it propagates through the Earth. And you can do exactly the same thing with the sun. You can look at how sound waves propagate through the sun, and the sun will end up vibrating and oscillating in a way that is very similar to what we do with seismology on the Earth, but instead of calling it seismology, we call it astroseismology. So there's an entire field that basically looks at the sound waves, in some sense, senses the sound waves that are bouncing around inside the sun, and if you want, you can convert those to a sound if you like.
So as some of the recent research then, it's confirmed some of the physical characteristics of the sun. Are they physical characteristics that we didn't know before fully?
So the work that we have been doing, there are a number of things that we know extremely well and exquisitely about the sun. We know when it was formed, roughly 4.5 billion years ago or so. We know we can age date it. We know the nuclear physics that is occurring down in the core. We know what's powering it in an exquisite way. We understand what the chemical composition, when you look up there, all you see to your eye is a yellow ball of gas, but 70% of that is hydrogen, 28% of it is helium, and then that other 2% is made up of varying degrees of carbon and nitrogen and oxygen and silicon and every element that you can possibly imagine in the elemental table. So we have a really good picture of exactly what the sun is made of and how old it is, what's powering it. So then in that sense, its physical characteristics are very well understood. Where our work comes into play is understanding how the sun got to have those particular characteristics. Stars are, like the sun, are not born in isolation by themselves. They're formed out of a gigantic cloud that maybe is 1,000 times the mass of the sun, maybe 10,000 times the mass of the sun, and under the effects of gravity pushing it together, you will get varying stars in varying numbers and varying masses forming out of that particular cloud. And that cloud may have been around for many billions of years before it actually compressed and formed stars. During that billion years or several billion years, as this cloud moves around the Milky Way galaxy, it's constantly being bombarded by other dying stars. When a star dies, it throws out a lot of carbon and nitrogen and oxygen and silicon and gold and silver and all these sorts of things which pollute that cloud. And so over the course of time, this cloud builds up in mass and it builds up in different chemical components. What you'd like to be able to do, when you look at the sun, you get a snapshot. You know, this is 4.5 billion years ago, this is how much gold there was, how much silver there was, how much hydrogen, etc. But you don't know what happened in the steps leading up to that exactly. So this is where we've come into play. We're starting to examine specific elements and specific what we call isotopes in meteorites that formed at the same time as the sun. And much like, say, an archaeologist would do on Earth, you would, say, pick up, if you were digging through the remains of something, you may do radiocarbon dating, and you will take the ratio of a specific, what we call isotope of carbon, say carbon-14 to carbon-12. This is how archaeologists age date, mummies and organic compounds. But the half-life, if you like, of these carbon-14 is very short. It's really valuable for age dating life on Earth, but it's not so great for age dating what happened to the sun before it formed. But we're using exactly the same technique, but using isotopes that decay on a much longer time scale. In this case, we're using isotopes of iodine and hafnium, and those particular isotopes get locked into meteoritic grains that land on Earth, and you examine them, and you can look at how much of these isotopes of hafnium and iodine there are, and you can use that to age date exactly when dying stars polluted the cloud out of which the sun formed. So this is really a first step in understanding what we call the prenatal phase, before the sun was born, which dying stars polluted and combined to form the cloud out of which our star formed. So this is what the new aspect of our research is.
So you actually do that by finding the particles or whatever on Earth?
Yep. So for me personally, my own area of research is computational and theoretical astrophysics. So I sit in front of a computer, I generate models of how galaxies like our Milky Way form, how the stars, how many are born at each step in time and how many die at each step in time, and how those metals get spread around, these elements get spread around the galaxy. So my work is more on the theoretical understanding and modeling. But the team that was involved in this particular research involves people who work on the nuclear fusion processes within stars, so the subtle details of the nuclear physics. There are those who work on effectively picking up those meteorites, putting them into in a laboratory astrophysics facility, and measuring, how many isotopes of iodine are there, how many isotopes of hafnium in this particular case, how many isotopes of palladium, some of these elements that sound exotic but which are part of our daily life. So it's a combination of what we call stellar evolution people, galaxy formation people like me, but as well as laboratory astrophysics and spectroscopists and traditional, if you like, nuclear physicists involved in the project.
And the recent research and the outcome of that research, is it something that the outcome of the research to yourselves you wasn't surprised by, or you were quite surprised by what you have found? I
think it is surprising what we've been able to do for the first time, as people had speculated as to what happened to our gas cloud out of which the star formed. But we've been able to tie down very exquisitely when the last time this gas cloud, as it moved through our galaxy, was polluted by a dying star. So we now know 30 million years before the sun formed, a star that was maybe 2 or 3 times larger than our sun ended its life and dropped a lot of gold and silver and carbon into the cloud that formed our galaxy, formed our sun. And we also know that 100 million years before the formation, that a more massive star, 20 times the mass of the sun, exploded and deposited a certain amount of material into the cloud. So we've been able to age date things for the first time, what happened before that cloud formed. So we are working, trying to exquisitely, very finely detail where that cloud of gas that formed our sun formed, how it got polluted, and that will explain the various abundance patterns of elements and isotopes that we see today. That is a new piece of the puzzle, And it's a critical one because perhaps in some sense, the most exciting project maybe that's going on in science today is the search for other planets around other stars, extrasolar planets or exoplanets. We want to know how many planetary systems are out there that might harbor, say, complex biological life like on the Earth. How many Earth-like planets are out there? If you want to study and search for these sorts of systems, it's fairly important not to just blindly look at stars and hope that you find something, but you need to understand that one system where you really do have a chance of understanding how did that solar system form? Why is there an Earth-like planet that sits in this sweet spot where we have all of this liquid water on the surface? How did that cloud that formed this planetary system and the sun come to be? What pollution did it see in the billions of years leading up to its formation? If we can understand at least one system really, really well, it helps us understand and make predictions as to how many Earth-like planets there will be out there.
I was going to ask that. Does it, because, you know, you say about what happened millions of years ago, etc., and to get that knowledge, does it then help predict the future? I mean, what do we know about the sun? Is it getting hotter? Is it cooling down? Is it getting bigger? Is it smaller? Will that help tell those things? In
that sense, no, not so much. We do. This comes back to one of your first questions about the physical characteristics of the sun that we understand. Because we understand its age really well, we know how much it weighs, we know what it's made of, we know the rate at which this hydrogen down in the core is going through this nuclear fusion process. Because we know how much hydrogen is there, and we know the rate at which it's being burned into other elements, that means we know how long it will burn for. So we have a pretty good handle on what the long time history of the sun will be. You know, we're basically at midlife right now. We're sort of 4.5 billion years in. Say another 4.5 billion years, we will have exhausted all of that hydrogen down in the center, and so over the next 4 or 5 billion years, the sun will continue to heat up a little bit. That's going to be a problem. I'm not getting into the topic of sort of
yes.
Global warming and that's a whole other kettle of fish. I'm just talking on long-term astronomical time scales. There's nothing you can do about that. The sun is going to heat up over the next few 100 million years, and ultimately, after a few billion years, it will have exhausted its fuel. It will stop looking like it does, and in fact, what will happen is the core will collapse. There'll be a new cycle of burning, but instead of burning hydrogen, it will start doing helium fusion. And what will happen is that's very energetic, and it pushes the envelope out. And so the sun will grow in size out to roughly about where we are, maybe somewhere between Earth and the sun, Earth and Mars. So in 4 to 5 billion years, there's not much we can do about it. We'll be sitting basically in the atmosphere of the outer atmosphere of the sun. That part is pretty well understood, and our work is more about winding the clock backwards and seeing how that cloud got to where it was, not so much where we're going in the future, because on a star-by-star basis, we do have a pretty good understanding of how long the sun will burn for and what its ultimate fate will be.
And do we have any knowledge of how many planets are out there that we've not yet discovered?
I think that there are... Planetary systems are incredibly common. There are almost every sun that we have, every star that we have surveyed shows evidence for planets. Now, they may not show evidence for things like Earth-like planets, but when you look at them, it's very common to see something like Jupiter, a very, very massive planet, crossing in front of it, or you can see the wobbles that a big massive planet like that imparts on the star. So we know planetary systems are incredibly common, almost ubiquitous, almost everywhere as far as we can tell. The real trick now is going to be how many of those systems have Earth-like planets, little terrestrial planets made out of rock, potentially sitting in that sweet spot where ideally where water can exist in a liquid form. That's where the next generation of surveys are. We're just tickling the edge of that right now. We are starting to discover things that really do look like Mars and Earth in very small numbers. So we do know that we have thousands of planets that are known, but there's only really a handful that you would say look like they're Earth-like in terms of where they sit, how close to the sun they are, to their own sun. That's really where the next generation, the next 10, 15 years or so will be aimed at trying to characterize how common those Earth-like planets are. Odds are they're very common.
And I mean, the key areas then of solar research today and the future is mainly around what we've just been talking about, or other exciting things to come in that research area? Are there many things that we don't know yet that we're going to discover by this research?
I think the field of solar system research and solar physics research it's a very, very hot and exciting topic. It's again, I'm working at it from the other perspective. For me, the sun and the stars in general are, for me, just a part of the Milky Way galaxy as a whole. So I use them as tools to understand how our galaxy forms. I'm less involved maybe in what's happening inside of the stars in some sense. So for me, they're probes of a larger scale. So I'm not really an expert per se in the solar and solar system physics, but there's an enormous number of satellite missions planned, and the European Space Agency has missions that are out there right now. If you've been paying attention to the news, there's a satellite going around comets right now, getting exquisite pictures of what's happening around a comet. You've got visits going to various planets in the solar system. There's lots of questions still about the issue of life and water on Mars. What's happening on Titan, what's happening on Europa. There's exciting things happening beneath the surface there. So there is an enormous field of solar system physics. I think the work that we've done shows that you can, just by picking up, if you like, meteorites on the ground and digging through them very, very carefully, you can actually build up a timeline, for what happened before the sun formed. Now we've nailed down two different events at 30 million years and 100 million years before the sun formed. We know what contributed and what polluted to that cloud at that point in time, but there's no reason why one cannot dig a bit deeper and look at some of the other isotopes that are inside of these meteorites. We've just sort of scratched the surface, but we've demonstrated you can really do this archaeological age dating of the solar cloud before the sun was actually formed.
Right. Our next door neighbour's son, S-O-N, when he knew you were coming in today, wanted me to ask you this question.
Okay.
Would we ever be able to invent special suits that we could actually travel to the sun in?
Whew. The trick is always going to be protecting yourself from the radiation. The intensity of that radiation can be pretty extreme, and there's an enormous amount of research that goes. In fact, this area of solar terrestrial physics, the link between the sun and the Earth, is critically important. I mean, you can see the effects of radiation through you see the ionizing radiation that leads to the northern lights. So the solar wind is having a strong effect on things like the ionosphere. Critically, it has a very big effect on things like satellites, and so almost all of the satellites that are up there now have to spend an enormous amount of time in their development and figuring out how you're going to protect all the electronics, because whenever you have a sort of solar flare, you can actually put out a lot of damaging radiation. And so it's not so much maybe the heat, if you like, in that sense. It's that intensity of the radiation that would be the critical thing that you would have to overcome if you really wanted to get that much closer to the sun. And the satellites that are up there right now spend a lot of time. There's early warning systems when if the solar flare is known to go off, some of the satellites will go into a sort of a hibernate mode and shut down their electronics, or put up solar screen to try and block it. And that is an issue for all satellites that are up there, whether it's weather satellites, astronomical satellites, or military satellites, communication satellites. This is the number one concern in terms of the interaction of us today, let's say, with the sun. And this research that's going on, I mean, it's a research team, I take it, that's worldwide with people around the world. So, I mean, do you communicate through social networks, etc., or do you actually come together? So I spent a year, 2 years ago on sabbatical, a research sabbatical down in Australia at Monash University. And this is where the project initiated. It brought together people who worked on these, if you like, these meteoritic abundances, Maria Ligaro, who works there, and myself, who works on the galactic evolution. And so that's where this project initiated. and then it brought in experts in various other fields to fill out where our own expertise was lacking. So the project initiated there with sort of face-to-face meetings, but since then, over the last, I guess, year and a half or so, as the project has developed, we have met through just various electronic means, virtual meetings. Sometimes it's just via email because we're 12 hours out of sync with those in Australia. Sometimes we'll arrange maybe every 6 months or so, we'll have a Skype con, so we just all get together on Skype and have a little chat. And so I think that's more or less the norm for most of the large international collaborations. They may have annual meetings where they do get together, but sort of the day-to-day interaction is through email, through Skype, these sorts of interactions. We may have some of my international collaborations will have sort of wikis that we sort of exchange our information through that means. That's.
And is the work that you're doing, just quickly, I just noticed we're running out of time. Yep. It's gone so quick. The work that you're doing here, is the work and the research here, is Uclan quite renowned in this area of research?
Yep. We have, in the field of, say, understanding the origin and the evolution of the chemical elements, we have observational expertise at the Jeremiah Horrocks Institute, in which I work in, and we have theoretical and computational expertise. And so that's my group, and other people within the Institute are very active in trying to understand the origin and evolution of the chemical elements. We're that's one of our areas of expertise, and it's been recognized by the international community and funding agencies. So I think we can put hand on heart and say we are one of the best in the world in that particular area.
Lovely. Can I thank you for coming in this afternoon? And it's been a pleasure to meet you. And thanks to Proffesor Brad Gibson from Uclan here in Preston.
Thanks, Huey.
Sunday nights from 9. Join Steve Franklin live for Preston FM's weekly request show.
Could I have some Pink Floyd for my mum?
Gino by Dixie's Midnight Runners.
Can I request 9 to 5 by Dolly Parton, please?
What a way to make a live.
Lavender by Marillion.
Sunday nights from 9. 103.2 Preston FM. The weekend stops here.